It is the 25th of August, about 7:38 a.m., continuing on with preliminaries, where we left off with the calculative on the residue classes mod 5. We now move on to another proposition. Let me check the camera real quick. Just make sure. There we go. All right. Well-defined operations. So, for each of these residue classes that we have here, A and B, within the set of all residue classes, we define residue class of A plus residue class of B to be equal to A plus B residue class of A plus B. Now, the same thing follows with the product. Here we go. These are well defined. Which is to say, the result does not depend on the choice of representatives. I'd say that's pretty well defined. It's a good definition anyhow. Now, let's look towards a rudimentary proof of this. Suppose A corresponds with A prime mod n, and B corresponds with B prime mod n. Well, then by definition we have n divides A minus A prime. And n divides B minus B prime. For the additive case, for addition, what we are given is A plus B minus A prime plus B prime, which which is equal to a minus a prime plus b minus b prime which is divisible by n. So the equivalence class a plus b is equal to the equivalence class a prime plus b prime. Right. For multiplication, AB minus A prime, B prime, is equal to B times A minus A prime, plus A prime times B minus B prime is what? A sum of multiples. Sum of multiples of n. Ergo, divisible by n. Thinking of this intuitively, if we want to say something is well defined, choose the representatives, plug them in, doesn't matter. You're still going to get the same sort of outcome, the same structure of an outcome, the same thing which obeyed the proposition as was laid out earlier. So, and that appears to be the case. Now let's look at a calculative example of this. Let's start to go place this different one. Oh, okay, that's good. Okay, so let's look at this calculative of addition, and multiplication. Mod 7. So, suppose we have 3 here, mod 7, plus 5. This is all mod 7. This would equal 8, which is equal to 1 mod 7. Right? Simple enough. And so we can say these things a lot more easily instead of just having to say residue classes over and over again. Whoops. Four mod 7 times 6. This is all within mod 7, of course, 24, which is equal to 3 within mod 7. Now let's go ahead and look at units, also known as invertible classes, which I think is probably a better name, but whatever. Well, we'll see. We'll see. So, another definition. Because invertible classes, that actually kind of defines what they do as a function, but in a way, units does. A class A mod n within the set of all residue classes is a unit. We'll just call them unit because that's easier to say. Is a unit, i.e., that is invertible if there exists B mod n, residue class B mod n, or just B mod n, with A mod n times B mod n equal to 1 mod n. The set of units i.e. invertible classes set of units, that makes more sense. Set of units, i.e. invertible classes, yes, is the set that we looked at earlier, these residue classes. Another proposition. This set of residue classes here is equal to the set containing equivalence class modulo A within the set of all residue classes such that the GCD of A and N is equal to 1. What's the proof of this? Well, I'm going to prove this both ways because we're trying to prove equivalency. So let's let the equivalence, did I say equivalence class? Residue class A within this set here, within this residue class. Be within this residue class, yes. Then there exists residue class B mod n such that A mod n times B mod n is equal to 1 mod n. By definition of multiplication in the set of all residue classes. This means A times B, it corresponds to 1 modulo n, mod n, which is to say, that is, AB minus 1 is equal to k times n for k integer. Any common divisor of A and N must divide 1. So GCD AN is equal to 1. All right, let's look at the other way. Conversely, suppose we already have that the GCD of AN and N is equal to 1. By Seuss identity, there exists integers x, y such that ax plus ny is equal to 1. Now, reducing mod n, we have ax corresponds to 1 mod n. Yeah, so you can see that if you rearrange that. So a mod n times x mod n is equal to 1 mod n. Therefore, a mod n equivalence class, the residue class has a multiplicative inverse and is in the set of all residue classes. Oh, whoops, nope, this is just the unit, okay. Is in the set of unit residue classes. Invertible classes. Yes, the set of units, yes, is within the set of units, yes. Right. Check the camera. Good. Now, let's look at a calculative. Just going to start calling it calc. This, of course, well, this is going to be units, mod 12. Positive integers. Less than 12. And coprime. Yeah, coprime to 12 are 1, 5, 7, 11. So, the set of units mod 12 is equal to mod 1, 1, 5, 7, 11, right? So we'll coprime. Let's check 5 squared, which is equal to 25, which is equal to 1. So 5 is its own inverse. Now let's look at one more calculative, and we'll call it a day. And it will be the end of the preliminaries in this textbook. We can move into the actual meat of the work itself. So let's look at a calculative example. Inverse via Euclidean algorithm. Let's find the inverse of 17 mod 60. Apply the Euclidean algorithm. And what you get is that 60 is equal to 3 times 17 plus 9. 17 is equal to 1 times 9 plus 8. 9 is equal to 1 times 8 plus 1. It's supposed to be a 1. I don't know what. There we go. Now, let's substitute back. What we get is 1 is equal to 9 minus 8, which is equal to 9 minus 17 minus 9, which is equal to 2 times 9 minus 17, which is equal to 2 times 60 minus 3 times 17, which, at the end of it, is equal to 2 times 60 minus, second, 2 times 60 minus, yes. This is going to be, this is mod 60, 2 times 60 minus 7 times 17. because that's what I put in my notes. Let's see. 2 times 60. Yes, 2 times negative 6. You got 6. 6. Why did I put negative 7? 6. Put 6 in there. What do you get? Hold on a second. What is negative 7? That's 53. 53. Okay. Okay. That's why. Okay. Hopefully I'm seeing things right. If I'm not, then, feel free to correct me. Thus, negative 7 is an inverse of 17, negative 7, which of course, 53. (17 mod 60), i.e. 53 mod 60 is the multiplicative inverse. Still trying to think if I did that right. Oh well, you can go back and check. But the basic structure still stands. That you can find the multiplicative inverse via the Euclidean algorithm. Alrighty then.